Continuing with section 3.1. Okay, let's pick up with determinants. All right. So what we're going to do is define determinants in a way that you certainly didn't do in sophomore linear algebra. Possibly you've seen this in other settings, applied math maybe. But we're going to need to discuss permutations and groups of symmetries on the set 1 through n. So standard topic in Introduction to Modern Algebra. We'll make some claims. We'll have to borrow a handful of claims from Introduction to Modern Algebra. First, a nice general definition of a permutation on a set. A permutation of set A is a one-to-one and onto function. That is a bijection, phi, that maps the set to itself. Sets don't have any structure. We're not talking isomorphisms or anything here. We're talking basically a function that jumbles around, in a sense, permutes the elements of the set A. There's no constraint that set A be finite or even countable for that matter. Our applications in here are big time involving finite sets. What we're going to consider is a set 1 through n. So these will be indices used to describe entries in a matrix. There are n factorial permutations on the set 1 through n. Okay, so if n is very big, the number of permutations is huge. So you might recall computations of determinants are computationally complex or computationally intense. It's hard to compute determinants without any shortcuts for big matrices. Here's the fact that we've already run across an n factorial that's going to arise in the computations of determinants, something very suggestive of that from your past experience with computations of determinants. Okay, to deal with these permutations, we're going to use a cyclic notation. We might permute, say, the elements of the set 1 through 6 by mapping 1 to 1, 2 to 3, 3 to 4, 4 to 2, 5 to 6, and 6 to 5. Notice, by the way, 1 to 1 and on to. All right, so indeed downstairs in the images we have 1, 2, 3, 4, 5, 6. Each is represented exactly once, as would be necessary in a bijection. Now we're going to represent this with this so-called cyclic notation. Element 1 is mapped to element 1. We'll represent that by parentheses deal here. It's a cycle of length 1. It simply means that point 1 is fixed by that permutation. More interestingly, 2 is mapped to 3, 3 is mapped to 4, and 4 is mapped back to 2. So these kind of cycle around 2 to 3, to 4, back to 2. 2, that's what the second cycle is. 2 is mapped to 3, 3 is mapped to 4, and 4 is mapped back to 2. 5 is mapped to 6, and 6 is mapped back to 5. We'll represent that with a cycle of length 2. So the length of a cycle is, of course, the number of elements in that cycle. We can multiply these permutations together by reading right to left, following the notation that's used in the Fraley book that we use in Introduction to Modern Algebra, where if we wanted to multiply this collection of 2 cycles together, we would do so as follows. Let's see where 1 is mapped. Well, first, 1 is mapped to 4. Then I look to the left and see if 4 is mapped anywhere else, and it is not. So 1 is mapped to 4. Let's see where 4 is mapped to. 4 is first mapped to 1. Then 1 is mapped to 5. And that's it for 5. So 4 is mapped to 5. 5 is mapped to 1. 1 is mapped to 2. 2 is mapped back to 1. And 1 is mapped to 6. So 5 is mapped to 6. So let's do that one again. So what I'm doing is I'm starting on the right. I see where 5 goes. First, it goes to 1. by this cycle. But this whole permutation also takes 1 to 2. So now I've got 5 mapped to 2. But 2 goes to 1. Now I've got 5 mapped to 1. And finally 1 goes to 6. And now I've got 5 mapped to 6. So you pick up the 5 that you're interested in and you follow it. It goes here. But that's not the end of the story, because here 1 goes to 2. 2 goes back to 1, and 1 goes to 6. So 5 is ultimately mapped to 6. How about 6 itself? Let's see, reading from right to left. 6 is mapped to 1, end of story. And we've got this little cycle, 1, 4, 5, 6. There's 2's in the story. What happens with the 2's? 2 is mapped to 1, and 1 is mapped to 2. And that's the end of the 2 story. So 2 is a fixed point. There aren't any 3's in this particular permutation. If we mean a permutation on the set 1 through 6, then I might throw in a fixed point of 3 as well. But just using the symbols that are introduced in this collection of 2 cycles, we'd produce it in an alternate form here. It's tradition not to write the cycles of length 1. So this 2 cycle of length 1 on 2 just says 2 is fixed. It's common notationally to eliminate that. I don't mind writing it all out to see all those symbols there, thus my concern over the symbol 3. Cycle of length 2 is called a transposition. And so what we've got here is a product of a bunch of transpositions written in terms of some non-transpositions, written in terms of cyclic notation. Notice over here the transpositions, they share a lot of points. They share some 2's between these. All of them have a 1 in them. On the right-hand side, I don't see any repetition of symbols. So this writing of the permutation as a product of disjoint cycles is a useful thing, an efficient thing maybe. It gives you a bit of geometric insight as to how the permutations work as well. But a cycle of length 2 is called a transposition, and in fact we can write any cycle as a product of transpositions. You do so as follows. Consider the cycle that maps 1 to 2, 2 to 3, n minus 1 to n, and n back to 1. Okay, we could write that as a product of these transpositions. 1 comma n, 1 comma n minus 1, 1 comma n minus 2, 1 comma, and you keep decreasing that second entry till you get down to 3 and to 2. All right, 1 should be mapped to 2. Let's check it. 1 is mapped to 2, and there's no 2's in the rest of this, reading from right to left, so 1 is mapped to 2. 2 is mapped to 1, but there's a 1 over here, and 1 is mapped to 3, and there's no 3's in the remainder of it, so 2 is mapped to 3. 2 is mapped to 3. 3 is mapped to 4. 3 is mapped to 1, and this next transposition, it would go right here, would be the transposition 1 comma 4. We had 3 mapped to 1 and 1 mapped to 4, and no 4's to the left of there. Indeed, 2 is mapped to 3. 3 is mapped to 4. N is mapped to n minus, n is mapped to 1. Yeah, n only occurs in one spot, reading right to left. N is mapped to 1, right. So it gets wrapped back around. So you can see how the 1 is used to kind of as almost like a holding bin. I throw 2 into that bin of 1, and then what's in that bin gets mapped to 3. So I'm kind of using the 1 in a special way to get the type of behavior indicated. But we can take any cycle, write it as a product of transpositions in this sense. In fact, every permutation of a finite set of at least 2 elements is a product of transpositions. You might kind of think of these transpositions in the algebra class. I describe it as imagining a bunch of cups sitting on a table, maybe with numbered balls under them. And they've got certain initial locations. And then you go and you grab 2 of those cups and swap their positions. That's what a transposition does in terms of these numbers. So I might start out with the balls in position, ball 1 in position 1, ball 2 in position 2, and so forth. And then I swap these cups 2 at a time, and I can produce any permutation of those numbered balls that you like. So there's an informal way of thinking about it. The formal way of dealing with it is done in orbit cycles and the alternating groups in section 2.9 and some notes for Introduction to Modern Algebra. But every permutation can be written as a product of transpositions. Every permutation can be written as a product of disjoint cycles as well, from which we could use this representation of those cycles to deduce this. It's not a hard thing to show either, but informally thinking about it in terms of balls under cups that are transposed around is not a bad way to visualize it. Another important property, establishing this is really no minor feat. It's done, I know we do it in the graduate algebra class, Modern Algebra 1. Another important property of transpositions is no permutation of a finite set can be expressed as a product of an even number of transpositions and as a product of an odd number of transpositions. All right. So I ain't saying that you can't write a given permutation in a bunch of different ways. What I'm saying is those different ways you can write a single permutation as a product of transpositions, it has a one property that is conserved. The number of transpositions you use is either always even or always odd. So if I look at this permutation up here, we've written it as a product of 1, 2, 3, 4, 5, 5 transpositions. Can you write this same permutation a different way? Yeah, I bet you I can write it as a product of 3 permutations. In fact, if you'd eliminate these two, you'd get exactly the same result. What this is performing is this interchanges 1 and 2, and this swaps them back. So really, these two transpositions multiply to give an identity. So we could actually eliminate those and we get the same permutation. Maybe couching this in a specific symmetry group would be a little bit cleaner. But if you go through with the products that we had, you'll get the same type of thing if you eliminate those two transpositions. Hey, so you can write this permutation as a product of 5 transpositions. You can write it as a different product involving 3 transpositions. Yeah, and 3 and 5 are both odd. So that's the thing that's preserved in terms of writing permutations as transpositions. We can classify them as either even or odd based on the number of transpositions that can be used to write them as a product of transpositions. The proof of that is actually tedious, quite tedious. See the graduate notes for proof of that. The senior level class, I think there's an outline of a proof, or maybe it's a homework problem in there, but it's spelled out in great vulgar detail in the graduate class. So this allows us to define a permutation as even or odd, according to whether the permutation can be expressed as an even number of transpositions or an odd number of transpositions. The alternating group, A sub n, is the subgroup of the symmetry group S sub n of all even permutations on the set 1 through n. So a little bit of group theory for you. We're going to see this alternating group, the even permutations, play a little bit of a role in computations of determinants when we define them using these symmetry groups. Okay, so super quick introduction to symmetry groups and alternating groups. Let's talk determinants. Okay, so we're going to define determinants, and we're going to define them using these elements of the symmetry group S sub n, where we talk about n by n matrices. To get there, let's go back to sophomore linear algebra and talk about taking determinants. Nope, I'm getting ahead of myself. First, let's look at some more examples of this even and odd stuff, and then we'll talk determinants. I want to link this stuff together with determinants, and to do so, we'll pull some stuff out of linear algebra. But excuse me, consider the set 1 and 2. You got 2 permutations on that set. The identity permutation, 1 is fixed and 2 is fixed, and the transposition 1, 2. You interchange the elements or you leave them where they are. Easy for a set of size 2. How about a set of size 3? 1, 2, 3. You could leave 1, 2, and 3 fixed. You could fix 1 and interchange 2 and 3. You could fix 2 and interchange 1 and 3. You could fix 3 and interchange 1 and 2. Or you could cycle them around. 1 goes to 2, goes to 3, and there's a different cycle that maps sort of in the reverse order. 1 goes to 3, goes to 2, goes back to 1. So that gives us 6 permutations. We said something about n factorial for this symmetry group a while ago. Yeah, 2 factorial is 2. We got 2 things. 3 factorial is 6. And we got 6 permutations here. 4 factorial is 24. Probably don't want to really mess with that because it's too big. Okay, so we want to take these permutations and write them in terms of transpositions and see whether they're even or odd. Clear up here, this one involves 0 transpositions, so it's even. This involves 1 transposition, so it's odd. For the permutations on the set 1, 2, 3, we could have the identity. We could write that as 0 transpositions or as 2 transpositions. So let's take 1, 2, 1, 2. 1 is mapped to 2, is mapped back to 1. 1 is fixed. 2 is mapped to 1, is mapped back to 2. 2 is fixed. 3 is not in the discussion over here. It's fixed as well. The cycle 1, 2, 3 can be written. We made a note above that every cycle can be written as a product of transpositions by using a bunch of 1s. This and the next representation of this other cycle represents that. 1 is mapped to 2. Yeah, 1 is mapped to 2. 2 is mapped to 1 and then to 3. So 2 is mapped to 3 and 3 is mapped to 1. There you go. So this cycle can be written as a product of 2 transpositions. So can this one. These 2 permutations are even as well. Where we fixed 1 point and transposed the other 2, of course, those can be written as products of single 1 transposition, and so those are odd permutations. Remember the notation of commonly not writing the fixed points down. I need to be aware of where we are if I'm going to do that. We're in the symmetry group S sub 3 in this conversation when I look at permutations on the elements 1, 2, and 3. Okay, so symbolically define sigma that takes these permutations, the elements of this symmetry group, maps them into the set -1 or 1 with the following rule. If pi is an even permutation from S sub n, define sigma of pi to be 1. If pi is an odd permutation, define sigma of pi to be -1. So we're labeling the even permutations with +1s and the odd permutations with -1s in this particular mapping. You'll recall in taking determinants, now let's talk determinants from sophomore linear algebra. Sometimes you had positives and sometimes you had negatives. Here's a determinant of a 3 by 3 matrix. You take products of 3 things at a time, sometimes with positives and sometimes with negatives. We're getting those positives and negatives out of these even and odd permutations, out of that sigma sign mapping that we just defined. So that's where the plus and minus signs are going to come from. I know you saw them come from somewhere else in linear algebra. You usually thought of like a checkerboard of plus and minus signs and introduced these in terms of that. They came out of cofactors when you did cofactor expansions, and we'll see that before we're done with this section, long section, this one. But determinant of a 1 by 1 matrix, A11 says the entry is just that entry itself. Determinant of a 2 by 2 matrix with the usual entries, A11 times A22 minus A12 times A21, the usual thing. Determinant of a 3 by 3 matrix, also the usual thing, possibly written it in a different order from the way it's introduced in sophomore linear algebra, but this is the same jumble of symbols you had in sophomore linear algebra. Also, collecting the ones with the +1 coefficient on the left and the ones with the minus coefficients on the right. I bet you somehow or other, these will be associated with even permutations, and these will be associated with odd permutations because they got minus signs that they lead off with. All right, so let's look at n equals 2. So I'm thinking about this 2 by 2 matrix, its determinant. I'm also thinking about S sub 2, the symmetry group on the symbols 1 and 2. Hey, there's 2 permutations on the symbols 1 and 2. Let's call them pi sub 1 and pi sub 2. Pi sub 1 is the identity. Pi sub 2 was when we swapped 1 and 2, the transposition 1, 2. We're going to write this determinant using permutations and these sigma things. Some observations. Notice we got a plus first and a minus second. The first index, 1, 2. First index, 1, 2. Actually, the same pattern holds down here. In the determinant of this 3 by 3, look at the first index, the first subscript on the A's. 1, 2, 3. 1, 2, 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. First index, we're always getting them in order. 1, 2, 3. 1 and 2. 1, 2, 3, and 4 if we do a 4 by 4. The second index, gee, I don't know. That's coming out of the permutations. Okay, so to expand this, we're going to take sigma of pi sub 1. Pi sub 1 is the identity. That's an even transposition. That's a plus sign. So this is an oddball way of saying +1. A sub 1, pi 1 of 1, times a sub 2, pi 1 of 2, plus sigma of pi sub 2. Here's pi sub 2, odd permutation. This is just a strange way of saying -1. A sub 1, pi sub 2 of 1, a sub 2, pi 2 of 2. Okay, so what we're doing is taking sigma of the permutation, a sub 1, permutation applied to 1, a sub 2, permutation applied to 2, and so forth. In general, when we expand this to higher dimensions, then we're taking the second permutation, sigma of pi sub 2, a sub 1, pi sub 2 of 1, a sub 2, pi sub 2 of 2. So we're taking permutation, sigma of a sub 1 permutation, a sub 2 permutation, a sub 3 permutation, plus second permutation, same procedure, plus third permutation if there is one, and so forth. All right, well, let's see, sigma of pi sub 1, even permutation, the plus 1 if you like. A sub 1, pi sub 1, pi sub 1 is the identity, so pi sub 1 of 1 is 1, a sub 1, 1. Pi sub 1 of 2 is 2, a sub 2, 2. Over here, sigma of pi of 2, that's an odd permutation, gives us a negative sign here. A sub 1, pi sub 2 of 1. Where does pi sub 2 map 1? Maps it to 2, interchanges 1 and 2. So pi sub 2 of 1 is 2, a sub 1, 2, and pi sub 2 of 2 is 1. Pi sub 2 interchanges 1 and 2. Which, lo and behold, that's the determinant of that little 2 by 2 matrix. So the way we're dealing with this is running through all the permutations in a group of appropriate size, the symmetry group S sub n, if we're dealing with an n by n matrix, and we're taking A1 something, A2 something, blah, blah, blah. And the something is being determined by that permutation. So how many of these little things are we going to have added together? One for every element of the permutation group. The permutation group S sub n has n factorial entries. Okay, that's a bunch. So we'll have a bunch of these things added together as you have when you calculate determinants. Let's do the same thing for 3 by 3. All right, if n equals 3, then we're going to have 6 permutations. Let's label them pi sub 1 through pi sub 6. And they are pi sub 1, the identity. Pi sub 2, the cycle 1, 2, 3. Pi sub 3, the cycle 1, 3, 2. These were the even permutations. We saw that on the previous page where we went through and wrote them as transpositions. Pi sub 4, the transposition 2, 3. Pi sub 5, the transposition 1, 3. Pi sub 6, the transposition 1, 2. This fixes 1, this fixes 2, and this fixes 3. And these were the odd permutations, as we saw upstairs. Obviously, they're odd. They're written as a single permutation. Okay, so what we're going to do is add up, like we did on a previous slide, except on a previous slide, is we only added 2 things together. Yeah, because n equals 2. And we only had 2 permutations. Now, we've got 6 permutations. Okay, so we're going to add up from 1 to 6 over all 3 factorial of those permutations, sigma of pi sub I, sigma of pi 1 through sigma of pi sub 6. And as we did in the case n equals 2, we're going to take that plus or minus 1, that's sigma of pi sub I, and multiply it by a1 something, a2 something, a3 something in this case. And the something is determined by the permutations. So what we're going to get out of this is a sum of 6 things of the form sigma pi sub I, a sub 1 something times a sub 2 something times a sub 3 something. The somethings are determined by the permutations. For example, let's look at this one. 1, 2, 3. Okay, there's pi sub 2. So what we do is we consider j equals 2. When j equals 2, it'd be the second term here. So here's the term we're going to get. J equals 2, we'll have sigma of pi sub 2. Pi sub 2 says it's even. We showed that upstairs, so we'll get a plus sign. This plus sign here comes from the fact that sigma of pi sub 2 is 1, because pi sub 2 is an even permutation. We wrote it as a product of, I think, 2 transpositions upstairs. Okay, so that's where the plus sign comes from. Now we're getting a1 something, a2 something, a3 something multiplied together. Yeah, that's why I pointed that out upstairs. We got a1 something, a2 something, a3 something. That's true for all 6 of these. They all read a1 something, a2 something, a3 something. Now for the something, that's coming from using, in this second term, this permutation. So we'll get a sub 1, pi sub 2 of 1. What does pi sub 2 do to 1? Maps it to 2. So we'll have a sub 1, 2. What does pi sub 2 do to 2? Maps it to 3. So we'll have a sub 2, 3. It maps 3 to 1. We'll have a sub 3, 1. And that's where the second indices are coming from. We're using these permutations to determine those second indices. You know you're going to get, we're going to generalize this in a rather obvious way. We'll take a sum over all permutations and a product over all appropriately indexed a sub i's. It'll be n of them probably. So you'll have n factorial, a sum of n factorial things, and each of those things will involve n of these double subscripted deals, entries of matrix A. And this thing out front will just take care of the plus and the minus signs. But if you'll go through that, and I would rather suggest you try to convince yourself that, that these are really correct. The last one, for example, let's see, that's associated with pi sub 6. 1 and 2 have been interchanged. Ooh, this is an odd permutation. Yeah, got a negative out front. Reads I sub 1, 2. Yeah, because 1 is mapped to 2. So that second index is the image of the first. A sub 2, 1. Yeah, 2 is mapped to 1 by this permutation. Right. A sub 3, 3. 3 is fixed by this permutation. That's where the negative sign comes from. That's where the second indices come from. That's why there's 6 terms, 3 factorial. That's why half of them are positive. These would be associated with the even permutations, are associated with the alternating group, A sub 3. And these are not. These are the other elements of the symmetry group that aren't even. These are the odd permutations. Anyhow, if you'll compare this expression, that's exactly the determinant of this 3x3 matrix as you dealt with it in linear algebra. All right. So with those observations, we're defining the determinant of an n by n matrix exactly according to that pattern. All right, so sunshade corrector. So, excuse me, low tech at Dr. Bob's Online University. Take A as a matrix. Square matrices, you only talk about determinants of square matrices. Have entries A sub ij. Let S sub n be the set of all permutations on the set 1 through n. It's a group, but we don't need any of the group structure. We'll mention inverses here in passing in some of the proofs. But that set of all permutations, there are n factorial of them. The determinant of matrix A, denoted determinant of A, sometimes you use these absolute value looking symbols. I prefer DET. But the absolute value looking symbols are common notation for determinants as well, is defined to be a sum over all permutations in that permutation group, sigma of the permutation, product from I equals 1 to n, A sub 1, pi of 1, A sub 2, pi of 2, A sub 3, pi of 3, up through A sub n, pi of n. So we get n things multiplied together here, just like we did upstairs when we looked at n equals 2 and n equals 3. They're preceded by a plus or minus sign, as we saw upstairs for n equals 2 and n equals 3. And we do this for every permutation. Of course, the best illustration of that is with n equals 3, because it's got a bunch of permutations, it's got 6 of them. 6 permutations, 3 factorial permutations, 6 terms. Half of them are positive, half of them are negative. There you go. Okay. So this is the pattern we had above. This is what we're taking as our definition of determinant. Super quick little observation on the history of this stuff. Determinants originally arose in trying to solve systems of equations. It's odd that determinants historically precede row reduction, because I don't know about you, but I'm so used to thinking of solving systems of equations by doing row reduction stuff. Initially, it was dealt with in terms of these determinant things. What's even odder is the idea of determinants precedes the idea of matrices, and we totally think of determinants as a property of matrices. But historically, this stuff with determinants comes out of trying to solve systems of equations, linear equations. But we'll take this as our definition. There's your little motivation. Hey, it's a definition, you know the story. You can't argue with a definition, but it should be motivated by something. So with those examples for n equals 2 and 3, there's just some motivation. I want to go to a different source, David Harville's Matrix Algebra from a Statistician's Point of View. Springer-Verlag book, Gentle's book that we're using is also a Springer-Verlag book. Springer-Verlag, excellent place for graduate level math books, graduate level everything books. But Springer-Verlag puts out lots of good stuff. This is probably sort of a rival to Gentle in terms of our perspective of a theory of matrices class with an eye towards statistics applications. But I'm going to go through and quote some results from Harville's book. These are, I don't think they're actually in, or they're not cleanly in Gentle's book. I'm going to label the results with letters. So the following stuff you see that's 3.1.c is a result from Harville's book. So I just introduced that notation to distinguish where we are as opposed to being in our designated textbook. Okay, So we want to talk about some properties of determinants A, and we want to talk about them using that definition of determinant we have in terms of those summations and all in permutations. All right. First, we'll claim that, just as an example, if we have an n by n, say upper triangular matrix, then the determinant is the product of the diagonal entries. Yeah, excellent property, tells you in linear algebra, well, if I could take a matrix and put it in a row echelon form, if it'll go in row echelon form, then it'll be upper triangular. And I can just read off the determinant by taking the product of the diagonal entries. Ooh, unless those row operations change the determinant. And sometimes they do. But you know how they do. And we're going to cover that shortly as well. But the claim is upper triangular matrix, say, determinant is the product of the diagonal entries. Similarly, for lower triangular, we're going to give an argument for upper triangular. All right. Determinant of matrix A, according to our definition, is this thing here. Sum over the elements of the symmetry group, sigma of one of those permutations, product of a sub 1 something, a sub 2 something, through a sub n something, something being determined by the permutation. Okay. First, if pi of 1 ain't 1, so this is pretty much an inductive argument. If pi of 1 isn't 1, then for some k with k between 2 and n greater than 1, we must have pi of k equals 1. Remember, pi is a bijection. A pi of something equals 1. If it ain't 1, then it's something, call it k, that's bigger than 1. All right, we're looking at it like this because then we've got a sub k pi of k, that's a sub k comma 1. Ooh, but we've got the situation where k is, where do I point? K is greater than 1. It's implied right here. So we've gone down to the kth row, it ain't the first row, and the first column. Upper triangular matrix, those entries are 0. If the first index is greater than the second index, we're below the main diagonal. And if we've got an upper triangular matrix, that entry is 0. So looking at upper triangular, in this case, we must have a sub k1 equals 0. So if you take the product from 1 to n of a sub I pi of I, all right, when I hits k, when I hits the parameter k, we'll get a sub k, apparently 1. Well, that's a 0 entry. Well, the product of all those things is going to be 0 because the kth one of them is 0. So the only way we can have non-zero for a product of this form is when pi of 1 equals 1. All right, we're going through a bunch of products. Yeah, if we've got a upper triangular matrix, then we're getting lots and lots and lots and lots of zeros. Think of it, half of the matrix is zeros. So the only way we can get products to be 0 is when pi of 1 equals 1. You can inductively show, in fact, similar argument. So now we're restricting ourselves to only permutations that fix 1. Giant step forward. Remember, we're dealing with n factorial permutations. We just slaughtered that n factorial down to something much smaller. But the only way we can get non-zero is if pi of 1 equals 1. All right, how about the rest of the product? How about the product in terms of the other n minus 1 entries? By induction, you can show that you'll need pi of 2 to equal 2 by a similar argument. Pi of 3 to equal 3, similar argument, and so forth. Pi of I equal to I for all I between 1 and n. So under the hypothesis of upper triangular, the only time these products are non-zero is when you're dealing with the identity permutation. So the only one of these terms that we get out that are non-zero, only one of these terms that we get out are non-zero, is when pi is the identity permutation. By the way, the identity permutation is an even permutation. So we'd have a product from I equals 1 to n of I times identity applied to I. That'd be I. So we end up with a product of a sub I. What happened to the sigma out front? Yeah, the identity permutation is an even permutation, and so sigma of the identity is 1, positive 1 plus 1. So there's, if you like, there's a plus sign out front. So the determinant of upper triangular matrix is the product of the diagonal entries. You want to do this for lower triangular, exact same kind of argument, except I'd probably interchange these indices here. It'd become a slightly more complicated conversation, but the same idea. A note, arguably a bit redundant with that, if we take an upper or lower triangular matrix, and if we get this product to be 0, then we can draw the conclusion again that pi of I equals I. We must have the identity. It's a slightly different approach to it in this comment. So the only permutation for which we get non-zero is the identity. It's even. We can draw this conclusion again. If we had, this is a real new observation here, if we had a diagonal matrix, diagonal matrices are upper triangular and are lower triangular. Diagonal matrix, only non-zero entries are along the diagonal. We're talking determinants, all matrices are square matrices. So for triangular matrices, we can draw this conclusion as well, if you like, because they're upper triangular or lower triangular. Okay, so with our definition, let's prove some stuff. So here's the plan. First, we're going to prove Theorem 3.1.a, the determinant of A equals the determinant of A transpose. Probably something you're familiar with from linear algebra, but we're kind of playing a different ball game here, because here we're talking determinants is computed with our formula for determinants. That's stuff about summations and permutations. So we'll establish that. And once that's established, claims we make about rows can also be justified about columns. Something I don't cover in sophomore linear algebra is elementary column operations, which I think is common in a sophomore linear algebra class. But some folks are using column operations out there, and certainly within the setting of taking of determinants, column operations can be a convenient thing. Now, what we want to do in the next 3 results, and we'll go through the proofs of these, is look at how elementary row operations affect determinants. What are the elementary row operations? I can multiply a row by a non-zero constant. There are 3 of them. I can interchange 2 rows, swap 2 rows. And I can add a multiple of 1 row to another row. Those are the 3 elementary row operations. We're going to see how those affect determinants. You've done this in linear algebra. We got a different definition. We're going to establish these things with our definition. All right. Suppose we start with a matrix A and we produce a matrix B. That's how these things are stated, by doing something to matrix A, doing some row operations to it. So the statement is, if n by n matrix B is formed from n by n matrix A by multiplying all of the elements of 1 row or 1 column, you might read that parenthetically, of matrix A by the same scalar, let's call it K, leaving everything else the same, then the determinant of B is K times the determinant of A. So we've multiplied, say, one of the rows of A by a constant K. That's an elementary row operation, if K is non-zero. And then we get the determinant to change by a factor of K. This is also true if we multiply a column by a constant. Probably something new to you from your linear algebra experience. I'd be a little bit surprised if you did column manipulations. But hey, if the determinant of A equals the determinant of A transpose, anything you do to the rows of A, you have some corresponding result for for doing to the columns of A. Row operations, column operations have the same kind of effect, according to Theorem 3.1.1a. We'll make a more rigorous statement about that when we prove 3.1.b. So there's multiplying rows by constants. What else do? You can interchange two rows. Theorem 3.1.c says, I know I skipped over some stuff, if an n by n matrix B is formed from an n by n matrix A by interchanging two rows or two columns, then the determinant changes by a negative sign. So row interchange changes determinants by a negative sign. Second elementary row operation. Third elementary row operation was adding a multiple of one row to another row. All right, here it's stated more generally. Here it says if B is represented, or B represents a matrix formed from an n by n matrix A by adding any row or column of, adding to any row or column of A, scalar multiples of one or more other rows or columns, then the determinant remains unchanged. So they haven't simply added a multiple of one row to another row. They've added to one row multiples of several of the rows, some linear combination of the other rows to that. So it's adding a multiple of one row to a row several times. So this is stated for adding a multiple of one or more rows. We could show it for one row and then claim induction. But this is your favorite result when it comes to determinants. If you're computing determinants, this tells you, hey, if I do these kind of manipulations, and these are the kind of manipulations you do to introduce zeros, when you do row reduction, they don't change the determinant. What I'd like to do is take a matrix and put it in maybe row echelon form. Maybe it's upper triangular. Then the determinant's easy to find. So I'll do some row operations. Those would involve interchanging rows. Ooh, that's gonna affect the determinant by a negative sign. Multiplying rows by scalars. You know, the only reason you'd want to multiply rows by scalars, it's usually to make the pivots one. I don't care what the pivots are, leave them not one. So that multiplying rows by scalars, if I just want row echelon form instead of reduced row echelon form, I might not even need that manipulation. And finally, this one, adding a multiple of one row to another row. That's how you get the zeros in there. That doesn't change determinants. So this is super good news. So the usual technique in linear algebra to find determinants is described as take the matrix and put it in row echelon form, doing so by only interchanging rows, and count how many times you did that, because every time you do that, it affects the determinant by a negative sign. Do it twice, it affects it by -1 squared. So keep up with the even or oddness of how many times you interchange rows, and then do the row subtraction stuff. And that doesn't change determinants. Then find the determinant of that row echelon form, which is relatively easy because it's got lots of zeros in it. If you're lucky, it's upper triangular. If it's not, it probably has a determinant of 0 because it's not invertible. But put it in a row echelon form, and then the determinant's going to be easy to take. So it's easy to define the determinant of that one that you've modified. Oh yeah, but you might have done some row interchanges, so you'll have to compensate that with a plus or minus 1 factor. So that's motivation on why you would want to look at these row operations. And you probably did the exact same stuff in linear algebra. Difference here is we're using this weird definition of determinant. We don't have a recursive determinant, recursive definition. We've got this definition in terms of permutations. In sophomore linear algebra, you probably had a recursive definition. And if you went through and proved any of this stuff here, it was probably shown by induction. So maybe you didn't get into that, and this is just sophomore linear algebra. So I tell you what, next, let's go through the proof of these. Let's go ahead and stop this video, and I'll have a special video with mostly just the proofs of the following in it. And we'll continue shortly. I'll see you soon.